So the Sustainable Engineering team has just rolled up at Cenex 2025 on a rather brisk September morning. And we are here to do a deep dive into the future of mobility in terms of alternative fuels and net zero. What we're going to be doing is taking a real close look at the components and subsystems and technologies and materials that design engineers in the mobility industry are going to be using to influence the design and manufacture of the next generation of vehicles. We've already got a whole bunch of video interviews lined up. We're looking at everything from cables and engines to batteries and test equipment, everything you need to engineer the future of net zero mobility. I am here on the Equipmake stand, and when I say stand, what I actually mean, we're outside of the hall because these fire engine units are effectively the stand this year, because these are demonstrating a project that Equipmake has been part of in terms of the electrification of fire engines, and in particular here on power sharing between the vehicles. So I am here with Ian Foley, who is the CEO of Equipmake. And if I can ask Ian just to talk us through the project, what it's all about, what problems it's solving, kind of where is it on the roadmap. So Ian, over to you.
Okay, thank you very much. So we were already working with Emergency One on the fully electric fire truck. So this vehicle has got our complete drivetrain, so it's our battery pack, motors, inverters, etc. But the challenge for fully electric fire service is how do you do extended pumping? So when you get to the fire, there might be multiple vehicles, but often there might be only one or two pumping. So what we've developed, in addition to our other product, is a very high power vehicle-to-vehicle charging system. So it means that if there are multiple vehicles at the fire, the one which is pumping can plug into one of the others, which is stationary, which is not doing anything at that time, and use its energy, and therefore it can carry on pumping for many hours.
Yeah. Interesting. And what sort of, from an engineering perspective, what sort of power are we talking about? What sort of currents and voltages are going to be moving between these machines? You know, what's the power requirements?
Yeah. So the power requirement for pumping is kind of, less than 100 kilowatts, but our system can do more than 200 kilowatts. So we've developed something that's very high power, because we also see other potential applications. So for example, off-highway, where people say, well, if you've got a off-highway vehicle, it's high power, it's not near a grid, how's that going to work for 24/7? Then you could have a Bowser vehicle. You could have a vehicle which is full of batteries, come up, plug in, and then that could swap over. So we've developed something which can do over 200 kilowatts, so it's well in excess of the requirements for the fire truck. It enables us to apply it to other vehicles.
Now I'm going to take a quick walk around, have a look at the hardware. Ian, feel free to jump in. This unit here, or a similar unit, has been removed from this vehicle to take a closer look at the Equipmake install. So from what I've seen today, if we can get the camera in here, here is one of, I think, 2 motor units.
That's correct. We have a tandem unit. So we developed a motor which is about the right size for a double-deck bus. That's about a 19-ton vehicle, and for heavier vehicles, we put 2 together in tandem. So this has the tandem motor. The other thing with having the twin motors is it's very high torque, so it can do steep hill climbing, things like that.
Okay. And then on here, we're looking at the battery pack. And then the Equipmake inverters will be in close proximity to these. You can see the cabling runs, etc.
Yeah, so the vehicle-to-vehicle charging system is in the pack in the middle there. That's in the grey pack. So as I say, it's a very high power system, and then battery packs on the side and inverters, etc.
Right, okay. Now, is this an electric pump?
Yeah, so that's a standard pump which has been electrified by fitting an electric motor to it.
Okay, yeah, brilliant. On this side of the vehicle, this particular unit here, where we can see the cables plugged in, this is one half, I guess, of the vehicle-to-vehicle charging infrastructure, or power sharing, however you want to describe it, and then cabled out into the vehicle on this side, where we've got the charging inlet over there. Yeah. So this is how 2 vehicles would power share at a fire or an incident where one machine is hard at work and the other machine is stationary and can share power to that particular project. So where is this on its roadmap? What happens next?
Right, so next is this vehicle will be finished testing, and then it'll go on to demonstration trialling with London Fire Brigade. So they'll be trialling this in real service so that we can check that in service we can deliver the performance that London Fire Brigade require. So that'll happen early next year, and then during the first half of the year we'll finish off all the validation testing, and then it'll be available as a product for sale.
Okay. And as you said, do you think there might be some technology transfer into other off-road vehicles and that type of market for this sharing capability?
Absolutely. We're talking to various different vehicle operators about it. But I think particularly in the off-highway sector, we can see a definite interest, and it's an enabler. But also there are other services which require extended operations. So anywhere where there's someone that requires extended operation, where they say, well, today we can't use EV because we need to run for 3, 4, 5 hours, then this will enable that to happen.
Excellent. Thank you very much. Thank you, Ian, for your time, and we hope to see you here next year with an update on the tests that have been running. We are on the Ford stand, and I could not walk past this without taking a closer look, because I know how much our audience and readers like to take a look inside these things to see how they work, because this is going to influence the design of e-mobility across the future. So this is referred to as a new electric power unit. I think I know what I'm looking at, because I have worked on the design of this type of system in the past, integrated electric motor and gear transmissions. However, the good news is I have Jim Fisher with me, who is the quality manager at Ford Halewood, and so he's going to talk us through the design of this particular product, what makes it special, and hopefully where it's going to fit into the vehicle infrastructure and move these EV vehicles forward. So, Jim, over to you. Talk us through this machine.
So, the unit's basically split into two halves.
Yep.
We've got the conventional gearbox side, and then we've got the electric motor side. The gearbox side kind of gets its origins a little bit to some of the automatic transmissions. Okay. So we've got a planetary carrier assembly with 3 pinion gears. There's a sun gear running through the centre, and then we've got a static ring gear, so that provides the actual gearbox element of it. Okay. We then come into the other side of our housing, where we've got the e-motor side. So here we've got a stator with a rotor inside. So the rotor is permanently magnetised, and then obviously the stator provides the drive. The kind of unique thing about the stator, and what we're seeing as technology moves forward, is that we have hairpins rather than traditional copper windings. So the hairpin technology that we employ in the power unit is really about improving the efficiency of the unit, taking out the space of fresh air within the motor to try and make the motor as efficient as possible. Kind of new technology into Halewood. This is a localization program for Ford, so it's been well proven with some of the initial launches, so we're just launching now.
Brilliant.
So that's basically the two halves.
Okay, some questions for you. I can see an output shaft here.
Yes.
Is this going to be transverse mounted or longitudinal? Is that outputting to a wheel, or does it go through? Right, yes, a wheel.
So it's transversely mounted.
Okay.
So in the Puma, it sits in the front of the vehicle, similar to a conventional ICE engine. In the Transit, so the Transit Custom, it sits in the rear of the unit, literally underneath the rear axles.
And this spline shaft here, is this running through the centre of the rotor?
It is.
So it's another output shaft from the gearbox?
Exactly.
Interesting.
Exactly.
So twin out, so you must have a hollow rotor.
Exactly that.
And the gearbox is feeding that shaft through the centre of that.
Yes.
Out to there. That's fantastic. Now, the other thing I noticed is that looks like an oil filter.
Yes.
So is the motor oil immersed, or is it like a cool jacket?
So it's a cool jacket, and then we've got the gearbox side immersed in oil.
Okay, so that filter there is running the oil in the gear unit. Right, gotcha. Oil cooler?
Yes.
Yeah, okay. What other questions have I got? I think that's it. So, motor, stator, windings, epicyclic gearbox, twin transmission output shafts, oil filter, oil cooler, 3
A three-phase input. I think that's it. Brilliant. Thank you very much. Thank you. In the latest issue of the magazine, we have been taking a look at the integrated heat pump technology that is being developed here. And we're lucky enough to have Alexander on the stand. He is Customer Chief Engineer at Bosch, and he is going to talk us through this heat pump technology, the reason it exists, features and benefits, and how it's going to be applied in future mobility. So, Alexander, over to you.
Yeah.
Tell us why and how.
So, to start with, the background that PFAS ban coming into play around 2030, 2035, and that's where the current refrigerant will be banned.
Okay.
So all OEMs, they need to switch to indirect system, and there are two solutions. It's either propane or CO2. Yeah. Bosch is investing into propane technology. If you just compare the cost, CO2 is too expensive. So you need to have an indirect system that works on propane. Indirect because, propane, you can't have a direct system with the propane. Which Bosch has quite a good experience in the heat pump because of all the thermal management system that we have. And Bosch is developing now the heat pump solution for automotive as well, which has some challenges. Obviously, a heat pump technology exists in automotive, but no one works with the indirect system at the moment. So that's what we're focusing on with SOP around 2030.
Okay. Yeah, so it's the indirect nature, which is technically interesting. We've got two heat exchangers here. I saw on the model there, on the picture, there's three. Does that mean that each of these serves a different system in the vehicle?
You can have a different layout.
Okay.
Basically, this is just, as you rightly said, there are two heat exchangers. You can have two of them to increase the performance on the system. But what Bosch believes in also usage of only one heat exchanger for the system, which works, and you don't lose the performance. It's a scalable solution. Okay, everything is here scalable. This is just an example, and this is just a 3D print. So you can have more performance on the e-compressor to make system perform better. You can have two heat exchangers, you can have one bigger, you can have potentially three, but honestly not many of the OEMs are looking at this because obviously you increase the cost significantly because apart from heat exchanger you need to add expansion valves, you need to add all this coolant system and so on. So yeah, and then the whole magic is happening, like as you rightly said, expansion, compressing, that's how you reduce the temperature, increase the temperature of the coolant. The flexible thermal unit, in simple words, this is just a box with the pumps and valves. So when the cooling coming from the heat pump, it goes to the passenger compartment, you need to pump it, you need to have valves. So this is a part of the system. You can see a lot of inputs and outputs here, and it goes into different areas, like e-axle, as you mentioned, we have also here represented. You need to heat it up, you need to cool it down, the same with the inverter. And then there is a third big part of the system, which is unfortunately not presented on the slide. They call flexible thermal unit for oil, and this is exactly what it's used for a battery as well. So you heat up the battery, you cool down the battery during the fast charging or whatever to prepare it. So this is part of the big system, let's say, and it's also presented by Bosch.
And these particular points here, cooling inlet and cooling outlet?
Inlet and outlet, and all the solution is scalable.
Just coming back to the unit here, as mentioned, this is a 3D printed model we have here. And I just wanted to say, given that I have a 3D printer at home, I can normally identify a 3D printed product. Not this time. I thought this was a cast finished product because the print of this is just immaculate. I'm guessing it's either a liquid, laser sintered or powder sintered process maybe, rather than the filament type machines I wear. But please do use this as an example of the level of technology and quality that 3D printers arrived at, which is transforming prototyping throughout the engineering industry. So yeah, fascinating. We are now on the fusion processing stand with Jim Hutchinson, CEO. And what we're looking at here
In terms of mega trends, I guess you could put these in the category of digitization, autonomy, electrification, because what fusion processing does is it designs and manufactures the electronic subsystems, should we call it that deliver the autonomy to these vehicles. And what we're looking at here, we've got 2 case studies here. This particular product here, which is an autonomous tug from Bradshaw Electric called the T800. And we're going to take a look at the sort of sensor array package on that. But then we're going to flip over to something slightly more sophisticated, which is this Alexander Dennis Enviro 100 AEV bus, where the platform has been designed, as Jim will explain, to either be ordered manually or to be fitted with an autonomous driving system. So I'm going to hand over to Jim in terms of why is all of this happening, why is it happening now, and what is the type of technology that's been integrated into these vehicles to make it happen, and then maybe where are we on the roadmap, when will we be seeing these out and about. So over to you, tell us, what's the background?
Well, I guess the background is that the base technology and all of the ingredients that we need to build these systems is there. So essentially it's the art of the possible, and we can do this stuff now, and we can do it safely, and we can do it efficiently. So the main drivers really are safety and cost. And by running vehicles autonomously, we can make them much more efficient, much more, and bring down the cost of operation essentially. So, and that applies to a lot of commercial vehicle operations. So whether you're running fleets of sort of tugs around a factory, or whether you're operating buses or trucks, it's similar economics. If you can reduce the numbers that you need to in order to drive those, and particularly that becomes more important in a world where we're seeing fewer and fewer drivers being available to actually drive. There's shortages on that front. Then it makes a lot of sense to move over to an autonomous operation. So essentially we've designed a system which has commercial vehicles in mind from right from the start. So that's what we've done.
In terms of the technology that you need to build into these vehicles, I'm assuming that you're going to have some form of central processing unit, which is going to have some software on it proprietary to you, and then a sensor array, and combining that all together, that gives you the autonomy. Now I noticed that it says level 4 on each of these. Could you describe level 4 and the type of technology you need to achieve that?
Yeah, so level 4 essentially means that the vehicle is safe to drive itself without an intervention from a human driver within a particularly defined operational design domain. So it doesn't mean that it can go absolutely anywhere you might choose. You can't just say, okay, today I want to go to Land's End, and off it'll drive you there. But within the operational design domain that has been defined, then it can operate safely and without human intervention. So in order to do that has specific requirements. So for example, things happen when vehicles are out and about. Fuses blow, power systems go down. So you need a level of redundancy on all of your systems. So you need redundancy on your sensors, on all of your safety critical systems, essentially, to do that. So that you know that if any of those occurrences do happen, the vehicle can then do something, put itself into a safe state without needing a human to intervene. Right. And that's the key, really. So, and that's really been core to what we've been doing, because ultimately the safety is a big driver for a lot of these things, as I've said, as well as efficiency. Safety is another core reason for doing it, and we can make the systems much safer by adding in those levels of redundancy.
Explain the architecture of the system. What are the sort of core components, and where does your intellectual property reside? What's special about it to you?
Yeah, that's a good question. So for us, our automated drive system is essentially all of the electronic sensors and software that are needed to drive the vehicle. So our system boundary essentially is at the CAN bus, which is where the data is actually then transferred to the vehicle actuators. So we're going down to quite a low level. So the system comprises of a whole range of sensors. So these would vary depending on the use case. So, you know, something like the tug would have a different number of sensors and different types of sensors to a large vehicle such as the bus. Right. But essentially, they will usually consist of cameras, lidars, and radars. So they're at the core. Yep. So they then feed their data into various processing units, and again there are multiple units, and this is partly down to the need for redundancy in the system. So you can't just have one which is a single point of failure, you have to have multiples. And so that then processes all of that data to work out all of the relevant information to the vehicle, so where it is, what's around it, what all of those things are doing, and then with a knowledge of where it's got to get to, what its mission is, essentially, it then can start to plan a path, and that will then get broken down to higher levels of detail, and ultimately that ends up in instructions to the steering, brakes and throttle in order to get the vehicle safely to where it needs to go.
Yeah, I was thinking in terms of control, steering, brakes and throttle. I think that's pretty much it. Yeah,
they're the main controls. Obviously, there's sort of various auxiliary systems that the system is also looking after, but that's obviously the primary means where you get the vehicle to where you want to go.
And in terms of redundancy, what you're talking about there, you're entering this kind of aerospace territory in terms of system redundancy, by the sounds of it.
A lot of the knowledge comes from that space. A lot of our engineers have worked in that environment previously, so there's been a lot of technology transfer in that space.
Okay. Are you having to install your own CAN bus, or can you operate within the vehicle's existing CAN bus infrastructure?
So we work closely with the vehicle manufacturer to make sure that the vehicle that everything is safe and secure. But we will work with what's there to the extent that we can, and then sometimes additional things are needed in place. But by and large, that's just something that we do as a matter of course in our support for the vehicle manufacturer.
Okay. One last question before we just have a quick look at the actual hardware we've got here is, dare I ask, is artificial intelligence involved in any of the decision making of the vehicles these days, or is that something for the future?
No, we do rely on artificial intelligence, and yes, that is a feature. There are various safety mechanisms in play which don't rely on artificial intelligence. So yes, and again that is necessary. We need to always know exactly how the vehicle will behave. But yes, we do use various artificial intelligence elements within the system.
So the way we're describing that these days when we encounter it is sort of AI but with guardrails.
Yes, that's a good way of putting it. Yeah, that's correct. Yeah.
Could you, just to sort of conclude, maybe just give us a little guided tour of the vehicles? Just show us some of the sensor products that have been deployed.
At the front, what you can't see is there's various radar units. They're all hidden, but there are some sensors that you can see, which such as lidars down the bottom and at the top, and also cameras visible. And then if you come around to the side of the bus, you can see at the top here there's the Cycle Eye. That's essentially a combined camera radar unit with several cameras and radars inside that unit. And then walking down the bus, again we've got similar camera radar unit at the top. And then on the back, another lidar unit. Okay. So there's several visible sensors on the bus, but there's quite a few more that you can't see.
Yes.
Then inside the bus, most of the kit inside the bus is actually hidden behind various panels. But yes, then we've got obviously all of the processing is actually in boxes hidden behind the panels. And then there's just an additional display panel for to assist the safety driver at the moment with the operation of the vehicle and ensuring. So that's worth stating that at the moment this vehicle is being operated in Cambridge with a safety driver on board, and that's really partly down to the regulation at the moment that's a requirement. But next year, all being well, we should have the means by which, in terms of regulation, by which we can operate on roads without a safety driver on board.
Yeah, really, that was my kind of last question in terms of the roadmap, this technology. So you're saying you're in real world road test with safety driver, but just months away potentially from the regulations allowing it to go fully autonomous.
That's correct. Yes, it should be possible to do trials without safety driver on board.
Okay.
And then by sort of later in 2027, it should be possible to get a vehicle fully qualified full driver out operation.
Thank you very much. A fascinating tour of the technology and the hardware. Here it is. Expect to see these types of vehicles out on the road soon. Okay, we are now on the TUAL stand, and I am with Philip Clark, who is the CEO of the organisation, and we're here to take a look at this. And this is a high-power charging unit, and I'll summarise it in my own words. This is designed to sit at the end of grids where there might be constraints on the amount of power, but you also might need to charge at high power, such as vehicle fleets. So the idea is that what this unit does is it has integrated battery storage, so it's a battery storage device essentially, and it is charging itself up when power is available to it from the edge of the grid, and then has the ability to deliver that at high power during vehicle charging. So that's a very simple explanation or summary from myself. I'm going to now hand over for a much more detailed description with lots of engineering data and some numbers, hopefully. But let's start with why TUAL? Where does the name come from?
Yeah, okay, so there are 7 different ways to mispronounce it. It was the worst bit of rebranding, but TUAL is the last 4 letters of perpetual. And the idea is we have an energy solution which never stops.
Okay.
I ought to point out as well, I'm the only non-engineer in the team.
Okay.
I'm very good in PowerPoint, so anything I say today is a little asterisk. But I did found the business. We interviewed 52 of the UK's biggest fleets because, I've been in, my background's energy, been building ventures in energy for 25 years. And I'm a car guy, and I sort of put the 2 things together, thought I'd get myself a very nice, fast Porsche Taycan. Turns out the problem that fleets have is with commercial vehicles, vans, trucks, off-road vehicles. And the thing they started saying to us was, commercial vehicles are different than cars. They require high power, every minute matters, we can't afford to have downtime. And vans often get taken home overnight, they can't charge there. Vehicles go to depots overnight, and we don't own those depots, and they don't have enough power, and we're sure as hell not going to upgrade sites we don't own. And 40% of commercial vehicles go out to remote and rural sites during the day, and there's no power there. And so we were trying to work out in all of these areas of persistent grid constraint, how are we going to solve this problem? The truth is, most charging sites are in use about 2 to 2.5 hours a day. So for 20 hours, 22 hours of the day, there's this grid connection sitting there not doing anything. There's energy just not leaking out. And we like battery coupled technology. This is a DC coupled charger, so once we've done the conversion from the grid into our battery, we don't care about the grid anymore. We provide the power from our battery through the charger to the vehicle. And that means regardless of what the grid's up to, we always deliver a high power charge that we control. So high power means in this system up to 210 kilowatts. We have a system for HGV available from Q3 next year, which will be 360 kilowatts. And we can take any input. One of the really clever things about this, we can take a single phase or 3-phase input, 16, 32, 69 amps, which means that really any available supply on any industrial or commercial site, we can plug and play. And one of the things, there are 3 things to it. We give you high power in unchargeable sites. We provide a level of remote orchestration, which means you don't have to worry about whether the system's working because we track it and monitor it in real time. It's an ultra high resilience solution. And the third thing is it goes in really quick and can be redeployed really quickly. So you'll see it's palletized. You don't have to do any civils, there's no trenching. It drops in, it sits behind the meter. If you've got a commando socket, you plug it in and you are live. Today it took us 18 minutes to commission the system. Now, there is not a DC power system in the world that does that. And so we're working with mission critical fleets, so blue light, energy networks, DNOs, water companies, all the kind of people who have real estate assets that they own and they need high power charging on, but who need to be able to do that in the worst possible situation. If the grid goes down, the police need to go out. If the grid goes down, the DNOs need to go and fix it. And so a battery integrated solution not only gives them charging where they need it, but it also gives them resilience if there are operational challenges with the grid as well.
Right. I'm thinking, talking to organisations like data centre operators, often remote locations, can't get power to those facilities. They're now building microgrid arrangements. Could you drop one of these into a microgrid like that to act as a charging platform?
Yes, you can.
Yeah.
So we don't care whether our source is AC or DC. And so solar array we can plug in as part of a DC microgrid, no problem at all. At the moment, in order to allow us to install quickly, this is a behind-the-meter solution that only does charging. And that means we don't have the DNO G99 type stuff. But inevitably, if you have a high-power battery in areas of grid constraint, you get asked to provide flex services to the local DNO. You get asked to provide uninterruptible power supply to the company you're sitting outside. And so all of these the system can support them all and will over time unlock them through software. It's software-defined hardware, so we can remotely unlock that capability when we've established our role in charging. One of the things that we find really interesting is how many people in mission-critical fleets do have real estate in the middle of nowhere. Think 10,500 telephone exchanges. They also have loads of vehicles they need to charge. But none of those sites can do high power charging today. Plug one of these in and they can.
Yeah, I'm seeing that now. So the vehicle could be charging while the person is on that job, repairing that infrastructure or whatever it is. I'm wondering, it's a lot of the stands around here, I'm also seeing electrification of marine environments. So what they're trying to do is get fossil fuel engines out of the harbours. I'm imagining something like this could just be dropped off on a dockside for charging vessels.
You're absolutely right. So it high-abs in, and so it drops off anywhere you need it. Batteries don't like being near the sea. That's the one challenge, but we can build some resilience there if we need to. I did an event with a company called Rad Propulsion, who are doing, I believe, electric boat propulsion systems. And they were telling me, because marine's not a world I know, they were saying how many marine and port environments are incredibly grid constrained. And again, if you have any kind of supply, we can just soak it up, we can harvest it round the clock, and then it's available as a high power charge when you do need it. So yeah, exactly as you say. They can go into different environments, maybe aviation. If you want to be airside, that's obviously a constrained environment. If you are in a military environment, that's often a difficult place to upgrade. And because this is designed to be a 99.99% uptime product, it's really good for those mission critical operations.
One last question about applications. We've done a lot of stories over the last 12 months about the electrification of, for example, mining equipment. Try and get fossil fuel vehicles out of underground environments for obvious reasons. And obviously charging those vehicles is a challenge, so no reason.
No reason. Quite a lot of off-grid vehicles run a slightly weird high amperage, low voltage charging dynamic. I don't know why. And so that means we'd have to evolve some of the charging spec. We use a standard CCS charging technology today. We will also use megawatt charging in the future. But the principle is absolutely the same. If you control the battery, you control the power supply, and then you just need to navigate it into the vehicle. Anywhere where you have a small source of energy, we can turn it into a high power output.
Is there anything special about the battery technology, or are you working with established technologies?
So we announced last week a strategic partnership with a Swedish company called Pickering. They're part of Vargas Holdings, a very big venture capital firm. The battery that we're using, we're the first to use their new architecture battery, which has got a number of advantages. It's LFP, but the really clever stuff is it has this self-healing property. So whereas most battery energy storage systems, if one module has a problem, the whole system turns itself off. This system is designed so if there's any problem with it, that module takes itself out and the rest of it stays working. And it gives us a level of resilience which you can't get with any other battery on the market. It's also very energy dense, very power dense, and gives us other advantages in the way we integrate. So the battery is quite advanced. It's not our battery.
No.
We're very proud, though, to use it in our system, and it's a key part of our architecture.
Right, we are here on the Ritherdon stand, and I am here with Ben Ritherdon. And what we're going to be having a look at is the RB Passively Safe Cabinet. Now, in the last issue of Sustainable Engineering magazine, the Cenex Preview, we did an article on this, so we thought we'd come and talk to Ben firsthand, find out some more about this particular technology. Ultimately, its goal is safety, because the idea is that the cabinet breaks away from its base unit if there was a collision. In addition to safety, there's also some sustainability benefits that I'd like to talk to Ben about. First of all, less damage to a vehicle that should bump into it. But more importantly than that, in terms of savings of energy and material, is the fact that the cabinets can be installed in locations without them necessarily being set back off the road or behind safety barriers. In theory, saving a lot of material and energy in doing that process. So I'm going to ask Ben just to introduce the concept to us, tell us where the idea came from, maybe one or two little engineering facts about how the cabinet breaks away from the base, you know, how you control that. The testing it's gone through, because a safety-related product, it's going to need some sort of certification, I guess. And a little bit more then about the rollout of this product. When will we be seeing them by the roadside, making roads safer and less material and energy intensive? So Ben, over to you.
Yeah, thanks, John. Well, the idea for the passively safe cabinet came from one of our customers, Weissler, and Weissler install weather monitoring equipment for checking weather conditions roadside. Now, they need to install that equipment in the right place to do the job. So if that equipment's on a high-speed road, because the equipment and the cabinets associated with it is potentially a hazardous obstacle, they need to find, one option is to find the nearest bit of crash barrier to install the equipment and the cabinet behind, or they can, if there's room, they can set the equipment, I think it's more than 4 meters away from the edge of the road. But if there's no barrier nearby, or there's not enough room to reposition the cabinet and the equipment, they're a bit stuck, and they can't put the weather monitoring equipment in the optimum place to do its job. So they came to us with that problem, and basically they needed what's called a passively safe or a crash-friendly cabinet that would do away with the need for the crash barrier or the need to re-space the installation.
Can you tell me a little bit about the concept of passive safety versus, I guess, active safety?
Well, the term passive safety is used in various industries and sectors. In the sort of the roadside or the highway sector, it refers to roadside equipment, which is designed to be more forgiving to a vehicle if the vehicle impacts it. Before we developed the passively safe cabinet, there was already an established range of equipment, but that was all things like signposts, supports, lamp posts, and that kind of thing. And those columns will be designed either to shear off, like our cabinet does, on impact, or some of them crumple up and absorb the energy of the car that way. So that was all an established kind of roadside equipment. But Weissler were unable to find a cabinet that was also passively safe, so that's why they came to us, as we were already supplying them with external enclosures and cabinets.
One of your colleagues was mentioning to me that not only is the kind of mechanism for bolting the cabinet down going to shear if a vehicle hits it, but also I hadn't thought about the electrical connections themselves. So there's some sort of quick release on that as well. Can you just enlighten me on that?
With the cabinet, there is the option for an electrical isolation system, and that it involves another one of our products. It's called the pole plug, and that's a quick release pull apart cable connector. So which does what as I describe it. So that connectors at the shearing interface of the cabinet. So that will break away, and rather than tear or damage the cable, rip the cable apart, it will just pop that plug and socket apart, which in itself is safer because you don't have exposed wires there. And there's also part of that, there's a box which also, when that loop is broken, it disconnects the contactor, so it also cuts the power to and all of that is housed in just below the shearing surface of the cabinet, so within 100 millimeters of the road surface.
Yeah, fascinating. Yeah, there's a lot more that goes into this than meets the eye, obviously, because I hadn't really thought about electrical isolation as well. Interesting. Now, I've seen videos of the product being tested. Where are you on the whole kind of test and certification roadmap?
Yeah, well, that's all complete, and there are already cabinets out there, or many cabinets roadside doing their job. There is, I guess, a European, a British BSEN standard called 12767, and that sets the method for testing crash-friendly products, and that was already in existence before we developed the cabinet for testing passively safe columns and things like that. So yeah, that sets out the method for doing a crash test, which involved remotely impacting the cabinet with a small car. And in our case, it was at 2 speeds. That was at 100 kilometers an hour and one test at 30 kilometers an hour.
And just to conclude, can you give me an example? Obviously, you had that key customer that drove the project with, I think you said, air monitoring type equipment. Can you give me maybe sort of 2 or 3 other applications of the type of equipment that this product might suit itself to?
Well, it is generally it's the customers that use it and already using it. They're similar to Vaisola. So Vaisola is road weather monitoring equipment. So they'll have a column with their equipment monitoring the road, and then the controller equipment for that in the cabinet nearby. The other ones are speed monitoring, vehicle recognition. So anything that's monitoring conditions or vehicles on the road, and the key is that it needs to be in a specific position to do that job. Right. So they can't always find the nearest bit of crash barrier to put that equipment. So it's not needed in every case. It's a bit of a niche product in a way, but it's in those situations where the on-site conditions they can't use an ordinary cabinet. So now we've got the possibly safe cabinet option to use in those scenarios.
As I mentioned at the beginning, one of the kind of key sustainability aspects to this particular technology is the ability to position the cabinet at exactly the location is required, but without having to put any of the normal safety infrastructure and safety barriers around it that you would if it was a fixed installation. What Ben's going to do is just give us a few numbers on the type of civil engineering that would be required just to protect one of the sort of standard cabinets. So yeah, Ben, just explain that to us.
Yeah, so I think that on a higher speed road, so I think that's roads with a speed limit 50 miles an hour or more. Again, an obstacle like a cabinet or a post, if you install those within, I think it's 4 meters of the roadside, it either needs to be passively safe, like our cabinet, or it needs to be installed behind a crash barrier. And I believe for an object like a hole or a cabinet, I think the requirement is 80 meters of crash barrier needs to be installed, which involves all the footings, the foundation work for that, and then the crash barrier itself. So it's a large cost saving, as well as all the safety benefits. There's a large cost saving potentially, and of course it reduces the carbon footprint, I guess, of an installation.
Yeah. That's absolutely fascinating. If you look at the environmental footprint or the CO2 footprint of different materials, looking at regulations like CBAM, for example, which is the Carbon Border Adjustment Mechanism, targeting just those types of materials, which is concrete and steel. Those materials have some of the highest carbon footprints in terms of manufacture and installation. So the ability to mitigate the need for that over an 80-meter period, over an 80-meter distance, is not a trivial saving. That's a significant saving, and one to be welcomed. I think you've answered all my questions. It's good to hear that they're out in the field, installing equipment where it needs to be installed, without all of that civil engineering that might need to go around it if it wasn't passively safe. And let's hope that the technology expands itself into other products and keeps even more people safe in the future. Thank you. And I am on the Intutech stand with Bob Matthews, and we're looking at some technology that is designed to allow the assembly and then disassembly of printed circuit assemblies for component reuse, upscaling, upgrading, all the sort of stuff that you need to keep product in field and working functionally as long as possible, and then to be able to recover those components if necessary, some of which could be very valuable. They may be ASIC circuits, they may be in BGA format, etc. All types of parts that are typically difficult to remove from a PCB are now much easier to remove. So I'm going to hand over to Bob. I'm just going to find out what the origins of this technology are, why did it all begin, what differentiates it from traditional soldering processes, some of the applications that it finds itself used in, and then we'll throw in a couple of little technical questions at the end that our readers enjoy. So Bob, over to you. Where did it all begin?
Well, thanks very much, John. Yeah, so it started actually in 2008. When Intertek came up with the concept of having this additive process that we actually call reuse, that allows the components to be adhered or bonded to the substrate material that can be released at end of life using our recycle process. Right. Now that was in 2008, and we went out to the marketplace with this, innovation idea. And of course, nobody was interested. Nobody was interested at all. So it's one of those bits of IP that you put in the bottom drawer of the engineering department. But then, of course, climate change, global warming, sustainability came to the forefront. So you open up the drawer, you pull out the technology, and we developed that technology to the point where early 2024, it actually went into production. And I'm pleased to say that the reuse printed circuit boards now are over 1 million out there in the marketplace. And that's contributed towards sustainability, and it's contributed towards other applications now starting to mature, because certainly in the automotive industry, which is why we're here at Cenex, there are EU legislation, draft EU legislations that are coming out, which include things like printed circuit boards over 10 centimetres square must be recycled at the end of life and put back into the circular economy. And Intertek, in essence, is the only company in the world that currently has a production solution to be able to produce a automotive printed circuit board and put into that application that will allow that EU legislation to be met. So we're now at a stage where we're looking at proof of concepts and demonstration samples, etc., to put into both the OEM and Tier 1 manufacturers, to allow them to be in a position to put it onto volume manufacture in 2030, 2035.
Wow. Just looking at the standard processes that would typically be used to assemble a printed circuit assembly, the majority will be soldered with a thermal solder. Now, conductive adhesives have been around for a while.
Absolutely.
I'm guessing the proprietary intellectual property is going to be in the way you get that to release, which others wouldn't. They would be a fixed adhesive. Can you give us as much information as you can about how that process of recovery works?
Yeah, so essentially there are two aspects. The first of all is the conductive adhesive itself, which is proprietary to us, and it's the chemical composition. So that's something that you could purchase from Intertek. Yep. And you can actually apply that to your existing production line. So if you already have a process with very, very little capex expenditure, you could actually manufacture reused printed circuit boards on your existing line. And that's a significant benefit to get it out into the mass market, or we can manufacture ourselves. So there's two options there. From the recycle side of it, yes, it is restricted, but essentially there are three elements of it. One element is that we soak the printed circuit boards in a warm water. We add some excitation to the process. And thirdly and lastly, we have a eco-friendly detergent material that helps us relax the bond between the component and the printed circuit board sufficiently enough for us to then typically we use a pick and place machine in reverse, essentially, to come along, identify the component, lift it off, and then put it into a tray, whereby those clean components can then be re-reeled and be put back into the circular economy. Now, each one of our printed circuit boards comes with a data tag, a QR code essentially, which allows the vision system to know when that board was manufactured, the bill of materials that manufactured, and we might even identify what the costly components are within that board. So there might be a decision-making process. Well, we only want 4 of those components because it makes up 70% of the value of the board, and remove those. And that's a really interesting point, because what we've also found is that when you manufacture printed circuit boards in volume, like a contract manufacturer would, you might manufacture let's say 100,000 printed circuit boards in a run, and then you might find that there's a fault with the boards. What would you normally do? You'd normally scrap them. You'd burn them, shred them, or bury them, essentially, which is what FR4 essentially equates to. But if we got the data code in there, and we've already identified, let's say 4 or 5 of the value components on that board, then when it comes to end of line and you see that that board is now a reject, you can at least go back and selectively take out the value components, which equates to maybe 60-70% of the value of the bill of materials, and put those back into the reel. So it's not just about end of life. It's about that whole circular economy of printed circuit boards. And the last point I'd make, if I may, is the fact that components are traditionally spec'd maybe 20-25 years life. So when a component goes into first life, it might be out there in the marketplace for, I don't know if it's a domestic product, 4 years, 5 years. If it's a car, it might be 10 years. But at the end of that life, what happens now is that WEEE regulations get buried and burned, and you're putting in the ground 10 years, 15 years worth of component life, with all the associated gold, etc. With this technology, if we can then recycle in second life, it means that it's essentially CO2 free and it's cost free. So the second or maybe the third application of that has significant value for not only the OEM, because by that time there might be a commercial interest in second-hand components, but also in the opportunity to save the planet. So we are definitely inspiring sustainability.
The way you're describing that, I'm also thinking there's less thermal stress on the components if they're not going through a soldering process. Are there reliability benefits from that potentially?
Absolutely. So one of the key facts that we found is that we can actually bond LEDs directly onto an aluminium substrate. But for high power LEDs, they have a different coefficient of expansion to that of aluminium. So when you have a traditional soldered joint on 2 differential thermal coefficients of expansion, what happens? You get minute cracks in the solder, which can attribute to a failure mode. But because of our conductive adhesive bonding technology, it does allow some flexation. So we don't get that. We don't get that. So it's also increasing the reliability and opening up the scope for the designer to put maybe ambient lighting directly onto an aluminium frame. It's a really interesting factor.
Fascinating stuff. I'm going to drill down now a little bit about the production process, because I'm thinking now from what you've described to me, I'm thinking if I was an electronics engineer, what questions would I be asking myself now? So a couple of questions. The design parameters, we talked about earlier, Gerber files, can I just take my existing PCB and hand it over into an adhesive bonded process? And a tricky one, which is if I've got a solder process, I might use, for example, automatic optical inspection, to check those solder joints. What sort of test processes would you use to test a PCB that's been adhesively assembled?
So it's a very interesting question. Thanks for asking that. So we quite often get potential customers, opportunities that come to us and they supply us with a Gerber files and a bill of materials and say, can we have this in a reuse in a sustainable format? Well, the answer is yes, you can, but we then have to revisit that design because there are certain aspects of it, like the pads, maybe the track widths, etc., that maybe have to be adjusted as part of our design process. So wherever possible, I really, really encourage potential opportunities, customers, to come to us at the very, very early concept stage, it's a design stage, because we're trying to save money, we're trying to save costs all the time. So the earlier that we can get engaged, the earlier we can influence the design, and the earlier we identify that it is actually a potential reuse design, the better for all parties, because we can get involved from scratch rather than taking a backward step to go forward 2 steps.
Yes.
So that would be my advice. The earlier you engage with us, the better.
Could you just enlighten me about how the adhesive is applied to the board? In the past, where I've used conductive adhesives, it's either been screen printed or digitally dispensed. Have you got a preferred process for that?
No, we use both. So we use both techniques, depending on the application, depending on the type of component that we're going to be assembling. Because some of the components, being so small, they actually are better off with a dot process, where we can actually formulate a pad using micro dots. Rather than a silk screen process. So really it depends on the design of the PCB and the components that can be used. It's dependent whether we silk screen, whether we dot matrix, or a combination of both.
Okay. Fantastic. Right, just to conclude, naturally it would be really interesting to know what the type of products are that are going to deploy this technology first. Are there any industry sectors or product types that it lends itself to in a kind of an upfront process? Who's going first?
That's another interesting question. And the answer really is, it's open to everybody. It's open to everybody. Some of the early adopters of things like HVAC, where interestingly we've been supplying those in volumes of 200,000 a year. And when we actually start to analyse the benefits and sustainability, we get to levels of 200,000 CO2e, which when you then think of a diesel engine car, that's equivalent to circumnavigating the globe 12 times, which is amazing. And I've got that component actually here. So that is that component there. So just a very small printed circuit board has such a significant saving on CO2e once it gets to end of life. And of course the components on that printed circuit board can then be removed and put back into that second and third life as well.
Sure. It's absolutely fascinating stuff. Thank you for your time, Robert. That's been really cool.
Pleasure.
And I think just to conclude, with the kind of sweeping legislation that's coming through in Europe now, I'm thinking eco-design for sustainable products. I'm thinking the automotive legislation that we talked about earlier, circular economy regulations, corporate sustainable reporting directives, all now feeding into this sustainability funnel and channeling this type of technology through onto the shop floor. So we should be interested to keep an eye on this as it unfolds.
And we're obviously interested with any potential opportunities out there for businesses that are going to that scope 3, scope 4 to contact us and share what we can do to meet their requirements in sustainability. Because at the end of the day, we are here to support what's a very, very important subject.
Excellent. Thank you very much, Bob.
Absolute pleasure. Thank you, John.
We are now on the Pickering stand at Cenex 2025, and I am here with Stephen Jenkins from Pickering Interfaces, and we're going to talk about an interesting angle on product sustainability. So one of the strongest attributes of sustainability is product longevity. So the idea that a manufactured product can stay doing its stuff for as long as possible. But during its life, especially in the electronics industry, things may need to be repaired, things may need to be remanufactured, things may need to be upgraded. And what's often overlooked is that most of those processes will require those products to be tested. And the question then is, what happens if the test equipment itself becomes unavailable or becomes legacy? Maybe the hardware, maybe the software, maybe even the cables and connectors. So what I'm going to do is ask Stephen how Pickering can help in those circumstances in terms of using its engineering capabilities to kind of fill the gap, I guess. So yeah, Stephen, over to you.
Thanks, John. Yeah, one of the things that we've been doing at Pickering, and we've been making cards for test and simulation for many years, is that we're not making any of those cars obsolete. We have a policy of, as far as possible, as long as the components are available, keeping those cards and manufacture. So for example, we have had customers in the aerospace industry come to us. They've been running a test solution for a particular aircraft type or airframe, and they're finding that the original supplier is now no longer producing the test equipment for that aircraft. But those aircraft are still flying, they still need to be serviced, they still need to be tested, checked out. So increasingly they're coming to us and asking us to fill in those gaps that the previous supplier or the original manufacturer of that test system will now no longer make for them. But because we don't obsolete designs, we're able to bring out even old designs from 25 years ago, still manufacture them, and we've been upgrading some of those designs to new components where we need to keep them in service for as long as possible.
Can you give us an indication of the types of sort of applications where that processor would be beneficial? So what sort of end products are you talking about?
Well, in the aerospace industry, for example, a lot of aircraft have sensors which are run by LVDT, that's linear variable differential transformers, or RVDT, rotation variable differential transformers. These are the transducers on the aircraft that measure the position of flaps, position of air brakes, undercarriage, and so on. And some aircraft, they've been around for a long time. They're maybe onto their second life. They've been a passenger airplane. They've now been converted into a freighter, or maybe been converted into a tanker. And the original producer of that ATE system for that airframe is no longer interested in manufacturing or supporting it anymore. So they're coming to us for cards that they can build a test system with. A modular test system in a PXI rack. And of course we're very happy to help them and to produce cards, produce modifications of cards that allow them to carry on and keep those older airframes, older aircraft in production or in use. And their maybe second life in the air freight market.
Yeah, fascinating. And we're talking there about, say, modular test equipment. That's kind of hardware side. There's obviously the software protocols and sort of software stacks for tests. But one other area I'm interested in where it often catches people out in the legacy environment is simply with cables and connectors. And I think you've got access to cable and connector manufacturing capability. So give us a clue. What's the weirdest, oldest connector you've ever had to connect to?
Oh, I mean, we just but everything really. I can't think of a particular type of connector, but we get asked to make a lot of cables. We have produced a system called Cable Design Tool, which is a free-to-use system. It's on our website. You can use it for free, and you can go on there. You can specify the type of connector you want. You can design your own connector. You can even specify connectors that are no longer in general manufacture anymore. And we'll make a cable up for you. Or you can just print off the datasheet and the work instructions yourself and make it yourself. But we have the facilities to make those cables as well. We've also installed a new injection molding machine. We've got injection molding facilities in our factory now, so we can injection mold the housings for cables that the legacy manufacturers are no longer interested in producing anymore.
Excellent. Well, thank you very much, Stephen. That's given us a good, solid introduction to how you manage legacy test environments. We'll revisit this story at a later date, I think. Maybe look at some case studies in the future. It'd be nice to do that, maybe in different industrial sectors and that sort of thing. So thank you for your time today. I am now on the Toyota stand at Cenex 2025, and I'm with Chris. And the reason we stopped here is that you very seldom get to see a Hilux looking like this, because what we're looking at here is the substructure of a hydrogen fuel cell prototype electric vehicle. And I thought it would just be really cool to ask Chris to walk us through the key components, so that people who are interested in this technology, wonder what's under the covers, can get a good idea of what's where. Now, I'm going to make a guess that that's where the hydrogen's stored. I'm going to guess that that's the fuel cell and the motor and drives at the back. But I'm going to ask Chris just to sort of talk us through the key components, see if I was right, and add a little bit of detail where you can.
Absolutely, thank you very much. So anyway, you don't really need me for this because you've got it exactly right. So there's 4 key components on the Generation 2 fuel cell system that we're using on this vehicle. And the first thing I'll say is that Generation 2 fuel cell system is already used in the Mirai passenger vehicle, which has been on the road in Generation 1 since 2014. So it's proven technology. And we've lifted the 4 key components that I'll mention now from that passenger vehicle. But as you've already mentioned, this is a prototype hydrogen fuel cell Hilux vehicle. So let's start with the hydrogen storage. So here we've got 3 large hydrogen tanks. The Mirai also has 3 tanks, but it's got 1 large, 1 medium and 1 small tanks. So where the Mirai carries 5.7 kilograms of hydrogen, with 3 large tanks, we carry 7.8 kilograms of hydrogen. Clearly the advantage being that we get a higher driving range of 400 miles. So then that hydrogen, which is stored at very high pressure, 700 bar, pressure is stepped down and the hydrogen is delivered to the fuel cell stack here at the front. So Generation 2 fuel cell stack, we call it a fuel cell stack because it's got 330 individual fuel cells stacked together, creating the fuel cell stack. So each one of those fuel cells, we supply hydrogen to one side, we supply air to the other side, and very simply, we try to bring those together. Think of it as a sieve, and the hydrogen tries to pass through that sieve. The electron can't, so it flows around a circuit. The flow of electrons, of course, is electricity. So each one of those cells generates a small amount of electricity, and then with the combination of 330 cells, you get a meaningful amount of electricity created to power a large vehicle like the Hilux. That power is then sent to the motor. Here in this prototype, it's on the rear axle. Again, this component is lifted directly from the Mirai vehicle, which is rear-wheel drive also. And then the 4th key component, which we haven't got on this rolling chassis, is the battery. You can see it in our vehicle. On the prototype, it's in the load deck, and that is a 1.3 kilowatt hour battery that acts for efficiency, capturing regenerative braking and allowing the whole system to be efficient. So the key point is that we've taken those 4 key components, the tanks, the stack, the motor and the battery, from the Mirai, and we're proving that concept within a different segment, the commercial vehicle segment. And now where we are with this project, we built 10 prototype vehicles in 2023. We tested them end of 2023 and start of 2024. And now we've taken the vehicle out to potential fleet customers to further test those vehicles, develop the vehicle further, and try and make a decision. Do we bring this vehicle to market? Is it technically capable to achieve the high specification and capability of a Hilux vehicle with a fuel cell system? And we're busy trying to achieve that. The ideal being that we copy-paste that technical capability from a diesel vehicle with 0 emissions and with the benefit of hydrogen fuel cell. So that's where we are with the project, and that decision will come soon about whether we can bring this vehicle, improved vehicle, to market.
Excellent. Well, thank you very much. I think our readers and our viewers will be fascinated to see under the hood of we got here. Thank you very much for an excellent presentation of that technology, and we'll obviously be keeping an eye on this. Maybe see you back here next year and see how those tests and the prototypes going. So thank you very much.